Guys, the objective of this video is to do an example for an undrained total stress analysis case. We do that by finding E subscript U, V subscript U. We then find the change in stress in the X, Y, and Z direction, and then we can find the strains in the X, Y, and Z direction. So just to provide some context, the question we're doing is for an undrained case, and we're just looking at a total stress analysis. That was the part A. In the next video, we'll do exactly the same question, but do an effective stress analysis and see that both methods provide the same answer. So now we're just going to be doing total stress though. So let's say we have a cube specimen of soil. So this is in 3 dimensions, and we get initial stresses of Ex equaling, sigma X equaling 100. This is in kPa. Sigma Y equaling 100, and we'll make sigma Z equal 100 as well. Let's then increase and decrease these values. So let's go like this. So say we were given that the new values now, so this is the initial, and now we've done something to it such that sigma X now equals 80, sigma Y now equals 110, and sigma Z now equals 120. So you can see that some values have increased and some values have decreased. Now the first thing we need to do for our undrained case, and because we're doing a total stress analysis, we know for a total stress analysis we need to use VU and EU. So now say we're given though E dash equals 5 MPa and V dash equals 0.2. We can't use these values for a total stress analysis. We could use it for an effective stress analysis, but not for a total stress analysis. So the first thing we need to do is find the right values. We know that VU is always 0.5, so that's fine, but we now need to find EU. So we know the formula in the previous video that EU equals 3 outside of E dash on top of 2 outside of 1 plus V dash. So we could sub the things in. That would be 3 outside of. Now it's given to us in MPa, but we're working in kPa, so we need to change that to kPa over 2 outside of 1 plus V dash is 0.2. So this would give us an answer of 15,000. So 2 times 2, so 15,000. 6250, and that's in kPa. Now that we've found EU and VU, we can go ahead and find the changes in the stress, and this is the total stress, so we can just find out by looking at our diagram. So we can see that in the X direction we went from 100 to 80, so it means it's reduced by 20. In the Y direction we've gone from 100 to 110, so we've increased by 10. And in the Z direction we've gone from 100 to 120, so we've increased by 20. Now we can use the formulas developed in the previous video, these formulas here, to find the strain in each direction. So the strain in the X direction is given by the stress, the change in stress in the X direction, minus V subscript U, change in stress in Y, plus change in stress in Z, over EU. So if we sub in our values, the change in stress in X is minus 20, our Poisson's ratio undrained is 0.5, open brackets 10 plus 20, so 10 plus 20, and this is all divided by E subscript U, which is 6250. If we plug this in, so it's 30 times minus 0.5 minus 20 divided 6250, we get minus 0.0056, which we can also write as a percent, so we just times that by 100, minus 0.56%. Similarly, EY, I'm not going to rewrite the formulas, but it would be change in Y, so it would be 10 minus Poisson's ratio, which is 0.5, open brackets change in X plus change in Z, so minus 20 plus 20, over EU, which is 6250. So you can see minus 20 plus 20 would be 0, so we're not going to get anything from there. So it's just going to be 10 divided 6250, which is equal to 0.0016. And then we could find the strain in the Z direction, which would be the change in stress of the Z direction. So 20 minus 0.5 outside of minus 20 plus 10. So minus 20 plus 10. This would be over 6250, and that would equal minus 20 plus 10 times minus 0.5 plus 20 divided 6250 is 0.004. Okay, done. So we found the strain in the x, y, and z direction. We did that by first finding the undrained values of E and Poisson's ratio, undrained. We then found the change in stress in the x, y, and z direction. And remember, these are all total stresses because we're doing a total stress analysis. So these are all total stresses. And then we just sub it in our formula for Ex, Ey, and Ez, where the only thing changing between each of them is the order of Ex, Ey, and Z. Poisson's ratio and the elastic modulus of undrained values are the same in every single case. Anyway guys, I would recommend watching the next video where we're going to be doing the exact same problem, but for an effective stress, where you're going to see we're going to get the exact same answer. Anyway guys, hope that helps.